Avogadro's number. Okay, enough of that. Let's go on. How about this? Just more space. Who's this? Helium. How many electrons? 2. Okay, how many protons?
2.
It's supposed to be 2. Okay, we see the electrons, but there's supposed to be 2 protons too. So what's the atomic number? Atomic number is what?
2.
Number of
Protons
in here, not number of electrons. Even though if it's a neutral atom, the number of electrons and protons are the same. Okay, let's move on. So, here's neon. You tell me, which one of these is happier? They're actually both happy. How do I know they're happy?
The outer shell is.
This one's happy because it has 8 electrons in the outer shell. This one is happy, it has 2. That's kind of the exception. We'll let that one go for a moment. So what is happiness? You didn't know you were going to get this discussion today. What is happiness? Filled outer shell with 8 electrons. If you have 8 electrons out here, you are a happy atom. And that's called the octet rule. O-C-T-E-T rule. Octet rule. Octet meaning 8. So you've got 8 electrons in the outside shell, and you're a happy atom. The octet rule. There's always exceptions. If you're helium or hydrogen, you don't have room for all that. But if you have 2 of them in your outside shell, then you're happy. So helium, it's happy. They have birthday parties and all that kind of stuff. Okay, so that's happy. This one's happy. Who is this? Neon. You know the neon signs. They're happy, colorful. Yes. Okay. So what was the rule?
8 electrons in the octet.
And it was called octet rule. Okay. So does that help us understand poor hydrogen? Is it happy? Now, what would make it happy? Another electron. Okay. Then it would be like helium, which is very happy. So we know what it wants. How could it get that? An extra electron. Covalently bonding could do it. Where you're sharing it, you didn't have to rob somebody at gunpoint. You got another electron to work with, you shared it. Okay, so let's take a look at carbon. Is carbon happy?
No.
How many outside electrons? 4. What would make it happy? 4 more. You're not going to get rid of these 4, it's just not reasonable. So you want 4 more. And you're not going to find anybody that wants to give you 4 electrons, so you share. We share and share alike, right? So we're going over here and look at not sharing first. Here's a marriage made in heaven. Look at this. Sodium and chlorine. Sodium has how many in the outside shell? 1. And it says, if I could just get rid of that lousy extra electron. And chlorine says, yeah, well, my problem is I need 1 more, and then I'd be happy, happy, happy. Octet rule. Well, marriage made in heaven. This one gives it to this one, and now they're both happy. Right? What kind of bonding does that? Ionic bonding, where you're transferring electrons. That wasn't sharing, that was transferring. But look how happy they are here. Now, they each have a charge. This one has an extra electron, has 1 less, so it's positive. This one has 1 more, so it's negative. But they're happy. And they like staying together, mostly. You put them in water, they would still be ions. This is what kind of bonding? Ionic bonding, okay? But let's go over here. Let's get back to the sharing thing, share and share alike. This is carbon who says, I just need how many more? 4. And the hydrogens are saying, we each just need 1. But if we get together, look at what we can do. We can pretend like we're all happy. The carbon has how many now?
Now I
8. And the hydrogens all have 2, so they're happy. Everybody's happy. What did you just make? Anybody know what you just made?
Methane.
Methane. Methane is not so happy. I mean, if you get that down in the coal mine, you can die from that methane. So what they do, poor little canary, they brought the canary down in the mine, and when it's much more sensitive to methane, methane doesn't smell. So the canary, when its feet are up in the air, you say, gotta get out of here, and they would get out. It was their warning that there was methane gas, because they couldn't smell it, and it would kill them. I don't know what happened to the bird. I'm hoping it was a good story, but I don't know. So the oxygens, they say, we could be happy if we had, we got 1, 2, 3, 4, 5, 6, we need how many more?
2 more.
2, and this one needs 2 more. Well, look at it. If they get together right here, then they all can say we've got 8 by sharing it. So what did we just make? O2, is that a compound? No, because they're not different. So this is diatomic molecule of an element. Oxygen, what you want? Oh, I'm really getting nitrogen, because nitrogen is 79% of the air. But that did the same sort of thing, but it had to have sharing of these 3. And then it was okay. So that's what we got, but they're not compounds. They're diatomic molecules of an atom, or of an element. Diatomic molecules of an element. Let's go here and see what we got. Who's this?
Carbon dioxide.
Carbon dioxide. It's all nice and symmetric, isn't it? Linear symmetry, bilateral symmetry. Look here, Mickey Mouse ears, go down to Orlando. You'll see them everywhere. Okay, so what's going on here? The blue ones are hydrogens, the red ones are oxygen. Who likes electrons more? Oxygen. So poor old little blue hydrogens didn't know they were going to agree to share. This is like wanting to share with your little brother. And he says, here you go, this is your part of the cookie. And you say, what? And he gives you this little piece and says, I'm sharing. You say, no, you're not. You're supposed to give me half the cookie. No, I'm giving you this part. That's his kind of sharing, okay? Well, their kind of sharing, the red one gets to hog the electrons more of the time than the blue one does. So that makes the red one a little bit negative, because it's got electrons more than the other one, more of the time. And the blue one's a little bit positive. So that's a combination here of sharing actually, but not real great. It's polar covalent. Is that important?
Yes.
Look at this. It sets you up for this. Water molecules find the other ones attractive. One here likes the red likes the blue likes the red. And so we have just made weak little hydrogen bonds. This is hydrogen bonding, okay? So it's polar covalent molecules, but they like each other in a way that sets up these bondings that are weak. But remember, if there are a lot of weak ones, you know, I think you've heard of it, if you want to break a pencil, it's one thing, but if you try to break a bunch of them all at the same time, it's another. Okay, well, all these little weak bonds go together and help be significant. Okay? So,
Why are those?
by what?
You said those are a molecule?
These are, the blue and the red ones, those are water molecules.
And not compounds?
And they are compounds. Yeah. These are not, diatomic molecules of an element. No, these are actually compounds. Thank
So
you.
is it like molecules and compounds interchangeable?
I'm not exactly sure of the exact definition of a molecule. I tried looking it up, it's a little hazy. So, compounds, I'm not going to get into it, but I saw conflicting statements. But when you talk about a compound, it has to be two different elements or more.
Yeah, I know that. I just had like molecules, more like.
Molecules bothered me because, they said like, I don't want to tell you.
Yeah.
It was confusing. I was trying to get clairvoyant, but clarity, that's it. I was trying to get that and I didn't really get it. And I didn't want to go there either, so. All right.
Somewhere it said, this is what she's saying, all, compounds are molecules, but not all molecules are compounds.
Yeah, because the diatomic molecules are not compounds. They're all the same element. So that's true. So you have to play those things off when you're trying to figure out what you want to say and how you want to say it. But they were saying like a molecule could just be a single atom. And that bothered me, didn't like it.
I think it kind of depends on which science is talking about, biology versus chemistry. Versus,
Right.
you know, 'cause-
Chemistry, I think, was saying it was, but
Cause like on the test, I had it, but,
you flipped what?
and it was like compound and molecule. That's what I, cause I didn't think about it as plus molecule.
Yeah, compound is, one thing you can go on, compound is two or more elements, different elements, okay? If you got two elements but they're the same, that's not a compound. All right. Any questions from the note sheet? Let's go back and see. Any questions down in here now? This is carbon 14. Oh, I know where I want to go, yeah. Carbon 14. What is carbon's atomic number? And you can look that up. You go to the appendix in the back of the book, and this is now page A25. So let's look at page A25. What's this thing called? Periodic table. We list all the elements. You said, if I was listing all the elements, it wouldn't look like this piece of junk here. It would be all nice and smooth and even. Well, this is the way things are. Question? This is in the appendix and it's A25. So the periodic table put all the elements in one table. That's very nice. Okay, you know, each time the book has given a new edition, they have another element or two or three. You say, where'd they do that? They made them. They can make elements in the lab. Say, what? Yep, they can. So you keep getting more and more elements. Like here, how many elements do we have? 118. Okay, and they all have their own code, their own symbols. You know about that. Potassium, sodium ions. You know about, well, ion would mean having a charge, but you know about these different elements. Okay? So, if you think this is bad, you've got to remember that this stuff here is supposed to be stuck in here. So, where's the space for that? You have to jam it in there, and then this whole chart gets squeezed out further. So, it's kind of confusing. But, remember how we had shells around our nucleus? Each of these represents a shell. There's a shell. Look where pure happiness is. Over here. These are called the noble gases. Noble gases. And they are very happy. They used to be called inert gases, but that means they don't react. But of course, somebody had to see if they could somehow force them to react, and they did. And now we keep calling them inert, because they could be forced to react with somebody else. If you're happy in your house, do you want to sell it? If you really love your house, you want to sell it? No, you don't want to change. So if you're happy, you don't want to change, and these are all happy, so they don't want to react with anybody. Okay? So they're not reactive much at all. In fact, we thought not at all. Now we know they can force them to do it under extreme situations, but that's kind of like, so, you know, why'd you do that? All of these, new elements that they've made, I thought, what's the point? You know, what's the point of making these things? Because most of them are radioactive. So what's the point? Then I read about how they could be used in certain ways that was different, and so maybe there's a point. Okay. Anyway, it's interesting to look at, think about, but we're not gonna get off on that too far. These are transition metals. Do you know any of those transition metals? What's this? Zinc,
Copper,
copper,
nickel,
nickel,
cobalt,
cobalt, iron,
manganese.
manganese, chromium, vanadium. That doesn't sound so familiar. How about cadmium? How about silver? And I saw the smiles. How about gold?
Mercury.
You probably don't, and there's mercury too. You've met up with that one. Gold. There was a man once who ran for office, and his name was Goldwater. So guess what his sticker was? AuH2O. That's convenient, isn't it? Yeah, kind of sticks with you. Okay. You like it? Okay. So anyway, there's some interesting stuff here. But is sodium happy?
No.
What would make it happy?
One more electron.
No, that's its problem. It's got one more than it wants.
Oh, it needs to get rid of.
Needs to get rid of that. Who needs one?
Chlorine.
Chlorine, so they got married, and they lived happily ever after. Because one needed an electron, the other one wanted to get rid of one, they made a deal. And potassium's like that. So potassium chloride would fit the bill here. Calcium, you would need 2 chlorines for calcium, because it has 2 to get rid of. So that's CaCl2, calcium chloride. So we're seeing the basis for chemistry, the interactions between the elements to make compounds based on this and the rule of happiness, octet rule. All right, well, we don't need to spend more time on that. Did we find?
Could you combine
Yeah.
any element and any other element so long as you can make the numbers?
They have to fit together right, like, I won't say you can't, because they can do some good stuff, but they're coming naturally together for natural reasons.
Yes.
Then you can make some good ones. These over here can go with these over here. And you don't get a potassium calcium or something like that. You have to be more creative with oxygens and other stuff in here. But they can do, there are a tremendous amount of compounds. And the organic compounds, oh my word, that's where you got all these chains of carbon and you stick in some oxygens, and we've done some of that. So you can make a huge number of organic compounds based on carbon.
Cause I know row 7, from the 4th onward is, non-naturally occurring elements. Those are actually synthesized.
Okay. Synthesized, unnatural ones. You have 92 natural ones according to the book, but not everybody agrees. But 92 natural ones. And the rest, 118, they're the ones you made in the lab. So they've done neat things there. They think that some of these may have some importance, but that's not all been determined. All right.